talk about starting with network solids. There's only two things I want you to know about network solids, and we're going to have to copy a few notes here, but it's only two things, so I'll let you copy, and then I'll tell you what those two things are, and we'll move on, and we shall never discuss the network solid again. All right, how's that? Or at least for until the unit test, perhaps. All right? So I think down here in compounds and whatnot, you have some stuff. All right, so we're going to talk about, just real briefly, network solids. What are network solids? They are substances, of course, can be found in very different forms. An example of network solids is something like, for example, pencil lead. Pencil lead is a bunch of carbons covalently bonded together. That's what we'll talk about in a second here. Covalently bonded together. Pencils are pretty weak. You push too hard and they break. Okay. Those same carbons arranged slightly differently in a different formation, still sharing electrons covalently, can be things such as graphite, which could be used as a dry lubricant, for example, or for example, you think about hockey sticks, graphite hockey sticks, and they can even be, you arrange them slightly different again, and you get ladies' best friend, diamonds, which are incredibly tough. Okay, in fact, so tough and so strong that they use them to mine into rocks, right? They put diamond-tipped drilling bits on, and they, oh my, the ladies are freaking out. Not the diamonds. And then they dig into the rock with the diamonds because they're so incredibly tough. All those things have carbon atoms joined to each other, but just in a different way. Okay, they're all covalently shared, the same, exact same, but just differently arranged, differently combined together. Okay. So in compounds, this is what you're going to have to know for network solids. Two things, all I'm going to ask you to know. In compounds called network solids, dozens or millions of atoms are of the same element, or perhaps two different elements are covalently bonded in a variety of patterns. They are covalently bonded, is what you have to know. Okay? Covalently bonded. And different network solids which consist of the same elements, so for example, pencil lead, graphite hockey sticks, diamonds, those three things would be called allotropes, is the other thing. They have different physical properties which are called allotropes. And those are the only two things I'm going to ask you about network solids, and now we're going to move on. Okay? Good? Yes? So that is all you need to know from that. Next. First thing we're going to talk about is intramolecular bonding. We've done this before. This is nothing new. It's a fancy term for covalent bonds. Okay? Intramolecular forces are forces that hold one molecule together. For example, one molecule of sugar is made up of 12 carbons, 22 hydrogens, and 11 oxygens. Or, for example, we could say that's an example of intramolecular bonding. All those atoms are covalently bonded together. This is what makes up one molecule. Okay? Makes up one molecule. Intra. C12H22O11. What makes up that, what holds that one molecule together is called intramolecular bonding. Okay? What holds each of those molecules together is intramolecular bonding, covalent bonding. Okay? However, if you think about sugar for a second, sugar. I have sugar. I have 1 grain of sugar on my fingertip here. How many molecules are in that 1 grain of sugar? Many? Lots? Cajillion? Babillion? Not sure. We could figure it out. I could tell you. Avogadro's number, etc., etc. However, it takes millions, babillions of molecules to make that 1 grain of sugar. But wait a minute though, even if I had a babillion sugar molecules, would you see them? If I laid them all out, for example, and just put them down, would you see them? Even if I had a babillion? No. So how do you see them? Well, they have to be linked together somehow. How are they linked together is what we call intermolecular forces. Okay? So what this is intra here, intramolecular forces, bonding, covalent bonding. But if I want to see all these sugar molecules in a solid form, what hooks this to this, and that to that, and that to that, and to the other billion of them? That's called intermolecular forces. And that's what we're going to focus on today, intermolecular forces. There is 3 different types of intermolecular forces. Okay? So, however, intermolecular forces are responsible for holding many molecules together. It's what holds all those sugars together. All right? It's responsible for making sugar a solid. There are 3 types of intermolecular forces, and they are listed coming up here. Okay? The first one we're going to talk about today is called dipole-dipole. Okay? Dipole-dipole is the first one. And all these things are very important here, what we tell you today here. In polar molecules. So this is polar. Okay, very important. In polar molecules, you have a negative end and a positive end to that molecule. Okay, I'm going to give you an example here coming up. Well, guess what? You don't have one molecule of it. You probably have a billion of them. And the negative end of one molecule is attracted to the partial positive end of another molecule. Remember, partial negative, partial positive, polar molecules. Okay? So the partial negative end is attracted to the partial positive of a different molecule. That's what constitutes, in this case, dipole-dipole bonding, or dipole-dipole forces. It's a specific type of intermolecular forces. Okay? This is all very, very important stuff here. I think we talked about that. It's possible to have many, many, many partial negatives attracted to many partial positives. Okay? And in fact, we're going to do a little example with HCl for a quick little example here. HCl is polar, last time I checked. If you want, you can even do this. Yes. 3.2, 2.2. This is a polar molecule. It's not AX2 or AX3 or anything like that. This is just simple. And I picked it for that reason because it's nice and simple. There's no tricks to this one. Difference in electronegativity. Electrons are not shared equally. Yes? So you get a partial negative and a partial positive into that molecule. That's intramolecular bonding so far. But we probably don't have just one. We probably have right? We probably have lots. We probably have times a cajillion of them. Yeah? Cajillion's made up number. Patent pending. Trademark. So we have many, many of these partial positive, partial negative, partial positive, partial negative, partial positive, partial negative. And each one of these molecules has intramolecular bonding, covalent bond, sharing electrons not equally. However, when these molecules get close enough together, is that going to be an attraction between those two? The partial negative end of one molecule is attracted to the partial positive end of a different molecule. Okay? And look, there's an attraction here, and there's one here, and there's one here, and there's one here. Okay? And that's only with 4 up there. Picture a cajillion. Okay? So these are what we call, in this case, dipole-dipole forces. Okay? Dipole-dipole because dipole means 2 poles. We have a negative end and a positive end to this molecule, just like poles on a battery. And the negative end of one molecule is attracted to the positive end of a different molecule. Okay? So, dipole-dipole, dipole-dipole, any blue parts there are dipole-dipole. That's what holds this molecule together. How well does it hold this molecule together? Well, that's something we'll talk about in the upcoming days. Okay? As far as that goes. Yes? Why is there what, sorry? That's the name of it, dipole-dipole. Two poles attracted to two poles, I guess. All right? So that's an example of what dipole-dipole forces are. Those are intermolecular between molecules. Okay? That one's not too bad, I don't think, right? Polar molecules, pretty straightforward. This would be an example of HCl again here, but you can see there's, in fact, 12 molecules on this one here, and you can see all the attractions that potentially could go on here. Okay? So there's just a nice diagram for you there, is all. All right? So that's dipole-dipole. Oh, hydrogen bonding. Hydrogen bonding also takes place in polar molecules. Okay? So it's a special type of dipole-dipole, and dipole-dipole, of course, is polar. Okay? So once again, we're talking about polar molecules. What's the difference between dipole-dipole then and hydrogen bonding? Hydrogen bonding only happens with certain elements. It only happens when you have H bonded to N, O, or F. So H bonded to NOF, or as I like to say, H bonded to FON, as in this class is FON. We're having FON now. Okay, apparently not. H bonded to NO or F, okay, or H bonded to FO or N, whatever. But H bonded to NO or F is a special type of bond. It's exactly the same as dipole-dipole, but in fact, it needs its own category because it's much, much stronger. Okay, all very important stuff here. Why is it stronger? And really, it starts off exactly the same way as any other polar molecule does. We're going to do an example with HF, hydrogen fluoride, because once again, it's the easiest. And we'll even actually start out here. I'm going to skip a bunch of stuff here. I'm going to go right to here. Okay. When we think about N, O, or F, the definition there for those is it's H bonded to a highly electronegative atom such as NO or F. It only works with NO or F, even though chlorine's electronegativity is slightly higher than NO or F. It only works with NO or F. Okay, we can talk about that later if you really want to ask or whatever. But it starts out just like any other polar molecule, right? Difference in electronegativity, partial negative, partial positive, yes? Okay. Partial negative, partial positive. And obviously, but we have a great difference in electronegativity here, a pretty good, decent one. Fluorine, nitrogen, oxygen, very high electronegative atoms, and they really pull on that electron towards it. So what we actually end up with here is we would say that obviously those two electrons are spending a lot of time around this fluorine here. So that they're not sharing very well at all. Okay, it spends a lot of time there. And what does that really leave us here? Well, we have this really electronegative atom. This is 4.0, like I said. This is only 2.2. Well, what does hydrogen look like? Hydrogen looks like this. One proton, and then it's got, that's the nucleus. You got your one electron out there, yes? Okay? That's what hydrogen looks like. It's only got one proton and one electron. Well, if that electron is really spending more time around fluorine, what are you left with here? So let's say that electron is spending way more time around the fluorine atom. Okay, not shared equally, obviously. What are you left with there? You're left with a bare positive nucleus. Okay? So you're left with a very positive nucleus there. So really, maybe what I should draw here is instead of drawing this hydrogen here, this is your one proton here. Okay? This is your very positive end. And guess what? It's also got a partial positive end to that. Fluorine here okay, is a very negative end to this molecule. And one of the notes we skipped over says, actually, this as well. It says that if you have lone pairs on the more electronegative atom, the lone pairs enhance the attractiveness, or basically you want to think of it as lone pairs enhance the negativity of that atom. Okay? So you got these lone pairs here, which make it a little more negative. Okay? And you got a partial negative charge. So, you know, compared to the last one where you had just partial negative attracted to partial positive, you still have that with hydrogen fluoride. You still have, in fact, HF, let's say HF here, oops, F. Okay, those are 8 there, count them. If you don't see 8, look harder, there's 8, okay? You still have this, there's no doubt about that. It's still opposites, partial negative attracted to partial positive. Because remember, hydrogen bonding is dipole-dipole, okay? Same thing. However, not only do you get partial negative or partial positive attraction, you get bare positive nucleus, very positive end, yes, attracted to very negative end here. Okay? Look, this is very positive. In fact, we're going to write this down. Very positive end, partial positive and bare positive nucleus. Okay, so on the hydrogen side here, right, you have your partial positive plus you have a full positive nucleus. So it's very, very, very positive at that end, yes? On this side here, partial positive, positive nucleus, very positive, right? Very positive, partial positive, and bare nucleus, bare positive nucleus. On the other side of HF, you have, on this side of HF, you have a very negative end. Because you have a partial negative and lone pairs. Okay? Yes? Any questions so far? So, very positive end and a very negative end due to H bonded to NO or F, very highly electronegative atom. The one thing you have to keep in mind is we're talking about hydrogen bonding, an intermolecular force. So really, when you draw me one HF, you have not shown me intermolecular forces. You've shown me intramolecular forces, what holds one molecule together. This is how it sets up, right? This is how hydrogen bonding starts, H bonded to NO or F. But intermolecular forces, hydrogen bonding, is between many, many, many molecules, different ones. So really, to show true hydrogen bonding, we need to do this kind of thing. Partial negative, partial positive, H to F, partial negative, partial positive, H to F, partial negative, partial positive. Let's do a little green here. Christmas time's coming. Okay. The green lines are hydrogen bonding. Yes? Between molecules. So this is in fact your hydrogen bonding. Hydrogen bonding. Okay? Now, is there any questions on that? Because I know that can be a little confusing. What's different between this one and the HCl one that I just drew in the first example? And the answer is, looking at this, nothing, right? They look the same. Look, let's go back to HCl. I'll show you. There's HCl. Yes? Here's HF. Well, that's messy. Where did it go here? There's HF, right? What's different? Well, they're both dipole-dipole, remember? Hydrogen bonding is a special type of dipole-dipole, a special type of polar one. So they're going to look the same. The difference is in the strength of them. Turns out this is so much stronger that it needs its own category. Okay? You have, remember, very positive end. This is a very positive end. This is a very negative end. This attraction is stronger than a normal dipole-dipole one. A lot stronger in some cases. This is a very negative end attracted to a very positive end. Yes? Very strong. Okay, that's hydrogen bonding. Much stronger attraction there. Likewise here. Stronger. Very negative, very positive. Okay? It's a special type of dipole-dipole that's strong enough to have its own category. Hydrogen bonding. How does it start? It's H bonded to N or F. Has to be very electronegative. More electron spends more time around the fluorine, which leaves hydrogen with a bare positive nucleus. That's the difference. Okay? If you go back to HCl, you don't have that because Cl doesn't have the same effect as N or F on hydrogen. Okay? So it has to be H bonded to N or F. That's how it starts. That's how, you know, when we talk about H, N, or F, you want to talk about the fact that the electron spends more time here around the more electronegative atom, which leaves hydrogen as a bare positive nucleus. That's how it starts. But remember, this is still intra right there, intramolecular bonding. Now it's the very negative end attracted to the very, very positive end of a different molecule. That's, in fact, hydrogen bonding. Okay? Let's go back and see what we skipped over here. Since hydrogen leaves the positive proton nucleus nearly bare. Hydrogen bond is the basically attraction between the exposed proton nucleus of the hydrogen atom and the partial negative charge on the highly electronegative atom, usually oxygen, nitrogen, or fluorine. So we got one hydrogen here, we got a different N or F here, and they're attracted to each other. Lone pairs on the electronegative atom enhance the negativeness or the attractive force. They enhance that. Okay? So that's what we talked about there. Lone partial negative and lone pairs enhance that attractiveness. Okay? Here's an example of water. I just want you to focus on the top one. We don't have to worry about the bottom one. But here's an example of water. This looks exactly like dipole-dipole to me. And in fact it is, because dipole-dipole and hydrogen bonding are both polar. Hydrogen bonding is just a stronger force. So this is a stronger force than dipole-dipole because it's H bonded to N or F. In fact, this is water. So OHH, OHH. Stronger, stronger bond, stronger bond, stronger bond, stronger bond. Okay? Than dipole-dipole. All right? But they look kind of the same because they are kind of the same. It's just that, once again, hydrogen bonding is that much stronger. Okay? Now, the third type of force we're going to talk about is London forces, or London dispersion forces. So far, we've only concentrated on polar. London forces does nonpolar. Okay? So, once again, dipole-dipole and hydrogen bonding are both polar. This is nonpolar. We're going to talk about, if we look at chlorine, bromine, iodine, fluorine, we'll talk about that in a second. Maybe not even today, but we'll talk about why those exist as different states. Okay, but those are all examples of nonpolar, right? You think about F2, for example. Yes? Most certainly nonpolar, yeah. It's a molecular element, yes, but it's nonpolar. FF, cancel each other out. Very simple ones we're doing here, of course. Cl2, Br2, I2 are all nonpolar. So when we talk about nonpolar, we can think about those ones if we want. Okay? So here's the deal. Okay? What do these intermolecular forces tell us? Well, they tell us the strength of how well one molecule holds to a different molecule, right? So when we think about HCl, going back to that one, I know this one's a polar one, yes. But how well does this one attract? This is dipole-dipole, or dip-dip, I like to call it. How well does, about these forces here, when we're talking about these forces, what holds them together? How well do they stick together? That determines the state that you have. If you think about gases, right, how much attraction is there between HCl and HCl, which happens to be a gas? There's not much, okay? They're pretty much floating around out here like this, you know, or dancing. As I can't go to the dance stand, unfortunately, but if I did, I'd do this. But the gases are floating by each other. There is some attraction between them, but as they pass by each other, they keep going their own way. Okay? So there is some attractions there, obviously. Look, this is partial negative, partial positive, is it not? Right? So obviously there's going to be some attractions, but they don't hold together very well, because if they did, guess what? The next state is not gas, but liquid. Right? Think about water. Water sloshes past each other, right? So there's lots of attractions there. They're sloshing by each other. Hey, I'm attracted to you. No, I'm attracted to you. No, hey, look, attraction, right? Sloshing by each other. Think about coffee, right? Rocking back and forth. Lots of attractions, breaking stuff, right? Then you think about solids. Solids, there must be a lot of good attraction, because solids, of course, are held together, right? They're locked in together. And there's very little movement. There might be a little bit of back and forth, but that's pretty much it. Okay? Solids are held together very, very well. So the intermolecular forces for the solids have to be quite strong. Okay? So we have different states, and that's what depends. What constitutes those different states? Well, it's intermolecular forces. That's what decides what's a gas, and what's a liquid, and what's a solid. Right? So that's what we're doing here. Gases are pretty weak intermolecular forces. Liquids are stronger because they're kind of locked together more. They make a liquid. Solids are pretty good intermolecular forces, and they're held together pretty well. Okay? So that's what we need to keep in mind here. All right, for those gases, liquids, solids. So London forces is going to help us with that a little bit as well. Okay, and that won't be till probably tomorrow. Gases require little interaction, little attractions. Liquids a little bit more. Solids, pretty good attractions between molecules. All right? The thing is, the one between nonpolar molecules is called London forces. Now, dispersion forces act between all molecules, but in nonpolar molecules, they are the only force that is acting on molecules. That's important. Once again, listen. Dispersion forces act between all molecules. All of them. Okay? Once I tell you what London forces are, then I want you to think about every molecule that you know of in the entire world. And I guarantee you, it'll have London forces in it. Okay? This is how you're going to explain London forces. Basically, this paragraph here. First of all, nonpolar molecules is what we're talking about here. London forces are nonpolar molecules. London forces are in polar molecules as well. We'll talk about how we're going to distinguish that later. Okay? They spontaneously form temporary dipoles. Not permanent like HCl and HF, because these are nonpolar, but they form temporary dipoles. Okay? So, keywords that you want to focus on here are temporary dipoles. Electrons are in constant random motion. Okay? Constant, rapid, random motion. Okay? And what happens is, as electrons go around and around your particular molecule, they're going to become distorted at one point. In other words, they're not going to be exactly where they should be around those atoms to basically be shared equally. Okay? When this happens, you are going to get what we call a temporary dipole. if the two electrons happen to be closer to this atom over here than this one, then this one over here gets a little bit of a negative charge, and this one has a little bit of a positive charge. And if we have, that's fine for one, but if we had a kajillion of those, and we had a kajillion, little bit of negative, little bit of positive, that attractive force all the way throughout that kajillion is going to be substantial. Okay? The unfortunate part is that little bit of charge doesn't last very long. Okay? So they're very instantaneous. They're what we call, another word we're going to say is induced here. And another key word here is that they called temporary dipoles. Okay? Polar molecules always have a negative end and always a positive end. London forces, nonpolar molecules, don't always have that. All right? And another thing we're going to talk about is the flickering process. They turn on and off like a flicker of a light bulb. On, off, on, off, on, off. Okay? So we're going to do that with hydrogen, because hydrogen's nice and easy. Hydrogen's got 2 electrons, obviously, being shared between those two. So hydrogen's nice and easy. Hydrogen, you know, if you think about the actual orbit of an electron, it goes in elliptical orbit, right? So here's my electron, here's my electron, okay? And they're going around and around, and they could be going around and around like this. So they're going all the way around, for example, like so. Sometimes they'll go like this, okay, et cetera, et cetera. But regardless, they're going to be making their ways around here, et cetera, et cetera. They're going to be shared between those two atoms. The thing is, though, okay, is there at one point, at one stage, you may end up with these 2 electrons. Now I'm going to exaggerate this. I'm going to do my 2 things here like this. I'm going to say one electron ends up here, and perhaps one ends up here at one particular moment of time. And when I say moment, I mean fractions of fractions of fractions of time here. Okay, it's going to last very, very short time. Okay. Well, when this happens, we get a partial negative and a partial positive charge, kind of like a polar molecule. Okay. And guess what? There's not one of these, there's millions of these. So we get this one and this one, we got this one and this one, here's another one here. We say that this molecule here induces or brings close enough to it any other molecule around it that happens to have that same alignment. So if this one here is a partial negative, partial positive, let's say just partial positive, partial negative, partial positive. And what you're going to end up with is this temporary attraction, temporary attraction. This temporary attraction, by the way, is called a London force. Okay? So they last for a very, very short, brief amount of time. We say that this molecule induces it, brings it closer to it. There's an attraction there. Or we say, you know what, there's going to be, remember, you got kajillions of molecules, and they're all packed pretty closely together. Is there another chance that you're going to find a partial negative and a partial positive in that big scheme of things somewhere? Absolutely. Okay? And it might be right next to it, it might be a little bit farther away, but there's going to be a slight attraction there for a very brief amount of time. So these are all London forces. The only unfortunate part is, while we were talking here, the electrons have now moved. So the electron's no longer there and there. Okay, in fact, I'm just going to, you know what, I'm just going to make another one here. Now the electrons are here and let's say here. Okay, so guess what? They are being shared equally here between the two of them. There's no negative and positive end. So this might be just fine. And guess what? Maybe this one particularly is neutral, kind of neutralish, and neutral as well. Maybe some of those down there now have formed a charge, temporary. Okay? This keeps happening, and then next thing you know, here's the beauty about this. We get over to, let's say, here, and now the right one has a partial negative charge and a partial positive. which once again brings anything close to it or induces the next one to it to become a, I'm not going to do any more than that, which forces the other ones to kind of fall in line, to be attracted to that one. Okay? Now, which one is it exactly? Is it a magical one? No. It's, like I said, it could be this one here now that's affecting those ones there. Okay? And it's just simply due to the fact that electrons are going around and around. That's it. Okay? And you will get, for a brief second, not when I say second, I don't mean second, you will get brief attractions there known as London forces. Okay? So once again, you get London forces. Now, once again, we have to talk about the fact that we have kajillions of these. So we have maybe a kajillion attractions for a very brief second, less than seconds. Is that enough to affect this molecule? And the answer is, it is. Okay? And in fact, if we have enough certain conditions, it can change it from hydrogen, by the way, is a gas. You know, if you think about it, fluorine's a gas, chlorine's a gas. Bromine is a liquid. Must have a lot of London forces, because London forces are the only thing in nonpolar molecules. Iodine is a solid. So iodine must have lots and lots of London forces going on there. Okay? And I'll explain what those are exactly. There's two factors that affect London forces. And when we talk about those, that'll explain why fluorine's a gas, chlorine's a gas, bromine's a liquid, and iodine's in fact a solid. Okay? So that's what London forces are. They are nonpolar molecules, form temporary dipoles. Electrons are in constant random motion, rapid motion as well, of course. For a brief moment, the distribution of electrons can be distorted so that one point of the molecule is slightly positive and the other one slightly negative. This momentary separation of charge, temporary dipole, induces a temporary dipole in the molecule beside it, so basically affects the next one beside it. This induced dipole can induce another one, etc., etc. This process, process continues throughout the whole entire, all the HHs, for example, all the hydrogens, okay? And it creates this flickering of dipoles. Turns on, turns off, turns on, turns off, okay? And so on and so on. You know, when we talk about inducing things, if you take a balloon and you rub it against your head and you stick it to the board, okay? You get this positive end affecting all the negative ends in the board. So basically it draws out, it doesn't want to, the positives don't want to attract the positives. The positives attract all the negatives. So the negatives come out towards the board, and remember the positive and positive would in fact repel each other. So the negatives come out and they attract each other, and that's what holds the balloon to the board, for example. Okay, it's the same thing with London forces kind of thing. If this one's a negative, it doesn't want another positive one beside it, wants another negative one. So it kind of helps bring that one closer, or in fact, maybe alters the other one so it comes a little bit closer, okay? Et cetera, et cetera. Okay? I think, let's see here. Do we want to stop? I think that's probably enough for you guys today. Well, one of the things you have to understand, like just this part right here, guys. Each of these individual attractions is weak, okay? Which one's stronger, do you think? Dipole-dipole or London forces? Dipole-dipole, absolutely. Because dipole-dipole is permanently got a negative end and a positive end. It's always there due to difference in electronegativity. Don't pack up yet. You got time. Always a difference in electronegativity. Okay? In fact, we got lots of time. We got 10 minutes. We might as well move on. Well, you guys are packing up. Well, let's move on. Yeah. I know. I changed my mind. It's always got a negative and a positive, and in polar, London has temporary, right? Temporary. They're not there for very long. Which one's stronger, hydrogen bonding or dipole-dipole? Yep. Hydrogen bonding's stronger. So basically, if we're going to like kind of rank these, we'd say hydrogen bonding's the strongest. Then we'd have dipole-dipole. and then we'd finally have London forces. Okay? Now, there's always exceptions to the rule. Is London forces, could it be actually stronger than hydrogen bonding? And the answer is yes, it can be. Okay? Can dipole-dipole be stronger than hydrogen bonding? Yes, it can. Okay? So we'll take a look at that, but generally, that's how it goes. Hydrogen bonding, dipole-dipole, and London is the weakest. Like I said, there's many, these London forces are very, very, very weak. But if you have cajillions of them, right, the overall effect is quite significant. And these interactions are the dispersion forces. Okay. Real quickly here, and I'm going to talk about this, we'll talk about more about this in depth. What decides how strong London forces are? By the way, London forces, let's go back to this for a second. Think about this. London forces, yes, they're in nonpolar molecules like HH and FF and CL, CL and BR, BR, etc., etc. Is there London forces in HCl? Now, HCl is a polar molecule, yes, polar. It's actually dipole-dipole. We did that example already. Is there London forces in this? Absolutely. Are those electrons stuck there? No, they're going around and around like they always were before. So when you say, well, what kind of molecule is this? I'd say it's polar. This is dipole-dipole. However, it does have London forces in it. London forces does affect this molecule. Okay? So we have to keep that in mind. London forces is the only force in nonpolar molecules, the only force. However, it's also in dipole-dipole. It's also in hydrogen bonding. Okay, it's always present. London forces affects many molecules, every molecule you can think of. Does it have electrons going around and around? Well, guess what? It's got London forces. Okay? So London forces affect everything. What are London forces based on? Really simply, there's two things that London forces, factors that decide how strong London forces are. The two factors are this one here. It says as the mass of the molecule increases. Really what we're talking about is, think about it. London forces involve electrons going around and around. Yes? So the more electrons you got going around and around, the greater the London force. So if you had, for example, look, hydrogen, how many electrons are going around H2? 2, right? Think something like iodine. Now, I'm not just talking valence electrons here. I'm talking about, do only the valence electrons go around and around? No. How many electrons does iodine have going around and around each one of those iodines? It's got, what is it? I can't see from here. 53, right? So if you think about that, there is a total of 106 electrons going around I2. Is there going to be a good chance for distortion when you got 106 going around? Is 106 going to be completely even every single time? No. There's going to be a lot of chance for that distortion to happen. The more chance of distortion, the more chance of partial negative, partial positive. The more partial negative, partial positive you have, the better chance there's going to be another partial negative, partial positive, the better chance of London forces you're going to have, the more of them you're going to have. Okay? So I don't like when the mass, same thing, but really we're talking about electrons. The more electrons you have going around, and I'm not talking valence, because they all go around, the more electrons you have going around, the better chance you have for distortion. The better chance of distortion, the better chance of London forces, simply put. We talk about size. That's what I'm talking about, the size of the molecule. How many electrons are going around and around. And the other one, which I'm going to save for tomorrow, and I'll review the electron thing again tomorrow, is called the shape. Okay? The shape, and that's again, you know, what do we talk about shapes? Well, hey, AX2, AX2E, AX3, AX4, right? Actually, I guess if we're talking non-polar stuff, regardless, I guess, but AX2, AX3, AX4, where X's are all the same, right? Turns out, the flatter the molecule, the more linear it is, the more contact area you can have, okay, and I'll show you this tomorrow, and the more effect you can have with London forces. So linear is the best at London forces. Spherical or AX4 stuff, where it's kind of like really big like this and spread out, not so good, okay? And I'll show you that tomorrow. I have two examples where the exact same formula, but they have different strengths. Okay, we'll stop there today.